Hello, I'm David Robertson, the Product Manager of the new SNE-Ignite Network Emulator. In this product demonstration video, my colleague Paul Hudson and I will showcase two key features of the SNE-Ignite, its low intrinsic latency and its transparent clock capability. First, let's address the challenge that O-RAN fronthaul network emulators face today. 5G O-RAN fronthaul networks are extremely sensitive to latency, i.e. delay, and also jitter, i.e. PDV or packet delay variation. Most network emulators available today aren't suitable for O-RAN fronthaul testing because they exhibit high intrinsic latency, high intrinsic PDV, and they cause delays in P2P traffic when large user plane packets are also present, which can lead to synchronization problems. Additionally, they lack sync key support. All or one of these issues can cause the ORU to lose lock, which prevents effective testing of vendor equipment. This is why we created the SNE-Ignite, which is specifically designed for O-RAN fronthaul testing. It features low intrinsic latency, as fronthaul connections are very sensitive to delay and low PDV, as many ORU devices are intolerant to jitter. SNE-Ignite also includes a transparent clock to ensure high-priority S-plane traffic is not affected by large user plane packets. In this demo, we're going to highlight two key features, the low intrinsic latency and the transparent clock functionality. So let's quickly go over the demo setup. We'll use the Paragon Neo in the time transmitter and time receiver mode to measure the performance of the SNE-Ignite's inbuilt transparent clock and to demonstrate its latency. Our first demonstration will focus on intrinsic latency. As previously mentioned, 5G O-RAN fronthaul testing requires low intrinsic latency, and many fronthaul connections cannot tolerate delays even as low as 8 microseconds. Therefore, using the Paragon Neo in time transmitter and time receiver modes will demonstrate that SNE-Ignite's intrinsic latency is less than 8 microseconds, the worst case in the O-RAN requirements. Now over to Paul for our first demo.
For this demo, we have Paragon Neo set up in transparent clock test mode, with SNE-Ignite acting as our device under test between the time transmitter on port 1 and our time receiver on port 2. This will allow us to make a measurement of the latency and PDV through Ignite whilst in idle mode with no map running. So using the Calnex analysis tool, we can see that the average latency through Ignite in each direction is around 6.8 microseconds with little variation. We can also look at the PDV, and we can see we're looking at around 16 to 17 nanoseconds in each direction.
So here we'll show the Ignite intrinsic latency is measured as only 6.8 microseconds, well below that 8 microseconds limit. And the PDV is measured and is only 16 to 17 nanoseconds in this test. That's a no impairment or filtering. So now we're going to demo a transparent clock. So the Ignite includes a one-step transparent clock mechanism. The SNE PTP and transparent clock ensures that the high priority S-plane traffic is not affected by the large user plane packets such as jumbo packets. And we're going to show you that the transparent clock meets the Class B specification. So over to Paul again.
We can use Paragon Neo's background traffic generation to simulate user plane traffic through Ignite while we also have S-plane traffic present. Using a map on Ignite, we can filter on the U-plane traffic and apply a delay of 10 microseconds whilst leaving the S-plane traffic unaffected. In this way, we would expect to see an effect on the S-plane traffic as it gets recombined with the impaired U-plane traffic on the output of Ignite. If we look at CAT, we can see the result of this, which is an offset in our two-way timer caused by our T1 timer, our forward timer, where we can see we have a lot of noise now on the signal due to that recombining of the packets as they leave Ignite. By enabling the transparent clock functionality, we can now eliminate much of that noise in that forward direction. And we can see the result of this directly on our T1 time error. We can also see our two-way time error as a result has come right down. This would ensure that an RU would maintain lock while that user plane traffic was impaired. With the transparent clock enabled on Ignite, we can use CAT to analyze the performance of that functionality. With the same setup, we can set the test environment to GA273.3 TC Class B. And we can see that the transparent clock meets the Class B limits for two-way time error, constant time error, and our components of dynamic time error for the high pass and low pass.
So here, transparent clock demo, we show that the transparent clock eliminates noise, both the T1 time error and two-way time error, ensuring that the RU would maintain lock, and that the Ignite transparent clock meets the G8273.3 Class B transparent clock spec. So at maximum time error less than 70 nanoseconds, constant time error less than 20 nanoseconds, and the dynamic time error passes both the high pass and low pass tests. So that enables S-Ignite to ensure that the high priority S-plane traffic isn't affected by the large user plane packets, such as jumper packets.
So thank you for watching this brief demonstration of some key features of our new SNE-Ignite Network Emulator.